Good. Okay. Welcome to the 2008 Rankin series of lectures. It's a great pleasure to have John Baez here from the University of California at Riverside to deliver these lectures. I'll just say a few words of introduction to the lecture series and to John. I'm not going to take up too much of your time because I know we're all passionate to hear John speak. Let me just say, first of all, that I'm grateful to the Board of Trustees of the Glasgow Mathematical Journal Trust for giving its support to this series of lectures. The series was introduced 2 years ago. First speaker was also from California. Yes, Percy Diaconis. His name just escaped me for a moment then. Percy Diaconis, also from California, so I knew John would remember who it is. So I don't know, this is setting a precedent that we'll have many more speakers from California, but it's certainly home to a lot of fabulous mathematics. And we're very pleased to have another Californian back here. The Glasgow Mathematical Trust supports activities that are a little bit wider than just the narrow confines of the business research interests of the University of Glasgow, and positively encourage us to look for mathematical activities that we can undertake which reach out to the wider community in Scotland, and that's very much in the spirit of Scottish education and the history of Scottish education. So that's part of the point here, that John's been invited to speak to us and is expecting to have an audience from a broad range of people with different interests and abilities in mathematics and different kinds of enthusiasms. John is a research mathematician, of course, in his own right, with some 80 publications in learned journals, author of 3 learned books about mathematics and its connections with physics. But for some of us, for me in particular, he's perhaps best known for his enthusiasm and ability to communicate his mathematical knowledge in lively, energetic ways. And for those people like me who enjoy surfing the web to find out nuggets of mathematical information, John's website is one I've come across very frequently, full of bristling with many different ideas about modern mathematics, interconnections with physics. So it's a particular pleasure to have John here in Glasgow this week to deliver the Rankin lectures today, Wednesday, and on Friday. And John's chosen to speak about his favourite numbers, starting with the smallest of the 3 today, the number 5. John.
Thanks. So I'm very honored to be asked to give these lectures, and I hear there's an overflow audience. That's even more exciting. I just want to warn the overflow audience that we actually have a little monitor listening in on you, so if you start snoring, I'm going to go over into that other room and wake you up. So don't think that I can't see you just because I'm not in the same room. So when I was asked to give these lectures, I thought, lectures about mathematics, what should I talk about? And I thought for a while, and then I came up with an idea. I could talk about numbers. And it may seem sort of like an obvious thought to those of you who aren't mathematicians, that maybe a mathematician might talk about numbers, but actually mathematicians think about a lot of things other than numbers. We think about pretty much any sort of structure that we can write down rules to describe, and in fact we get so sick of people making fun of how we're interested in numbers that we like to tell each other, mathematics is not just about numbers. We like to say that over and over again, but mathematics is also about numbers as well as other things. And so I thought it would be sort of fun to actually admit it and to talk about some numbers and to talk about some very specific numbers. I'm going to talk about the numbers 5, 8, and 24. So today I'll talk about the number 5. And part of the point there is that it's a very interesting thing that different numbers have different personalities. In other words, it's as if each number has its own kind of force field radiating out from it that influences the things that it affects, and they interact with each other and do combine in strange ways. And some numbers are more interesting than others. Some numbers do really wonderful, amazing things, and others, they just don't seem to do anything very exciting. Maybe we just haven't found out what's so great about those numbers. But the particular ones I'm talking about are ones that I've thought about a lot because they have a lot of interesting things going on with them. So 5, if I tried to explain its personality in words that have to do with people's personalities, I'd have to say it's difficult, it's sort of awkward, sort of spiky and angular. It just doesn't like to fit in with a crowd. It's sort of rebellious in some way. It's not really the best way to describe the personality of a number, is to use the kind of words you'd use for a person. But that's how I try to say it. And so let me try to explain why that works that way. So the simplest way to see it, I guess, is just to think about what are called regular polygons. So those are polygons with all the sides having the same length and all the angles being the same. So like a 4-sided one's a square. And you can have them with any number of sides that you like, but 5, you'd have to say, is the first rebellious one that refuses to tile the plane. So what do I mean by that? Well, if you take equilateral triangles, you can cover the plane with equilateral triangles. And the reason why is because if you look at the angle of an equilateral triangle, it's 60 degrees, so 6 of them can go around and add up to 360 degrees, and they fit in nicely together there. And so you can just keep laying them out like that in this pattern. And this is a type of pattern you've probably seen somewhere or other. People like to use these patterns for tiles and things like that. Okay, so that's 3. For 4, then you have squares. Squares are even more conformist. I mean, everyone has seen more squares than they want probably by now. People love squares for some reason. And so the angle of a square at the corner of a square here is 1/4 of 360 degrees, namely 90 degrees. So you can fit 4 of them in, and it works out fine. If you go up to 6, well, 6 is also fine because a hexagon, a regular hexagon, the angles are 120 degrees, so 3 of them fit around a corner, and that works out fine. Now, you could go up to 7, but because 3 just barely fit, because hexagons just barely fit, when you get up to heptagons, 7-sided shapes, the angle's too much. So those are too fat, so they don't cover the plane. They don't tile the plane. There's just not enough room, but that's sort of obvious, so we'll excuse them. So 5 is the one that I skipped over, and for 5, the problem is that they're sort of too big and too small. So the angle here is too big for 4 of them to go around a corner, but it's too small for 3 of them to fit around. There's this little gap here. So that's what's the problem with 5 in this case. And so, in fact, you can show that there's no way to make a pattern of tiles that repeats itself in 2 different directions. That's what I mean by periodic tiling, that has 5-fold symmetry. In other words, that if you stand at various different points, you can see in 5 different directions it looks just the same. So 5 is very different than 3, 4, or 6, where you can get that kind of periodic symmetrical tiling.